A physical constant is a physical quantity that is generally believed to be both universal in nature and constant in time. It can be contrasted with a mathematical constant, which is a fixed numerical value, but does not directly involve any physical measurement. There are many physical constants in science, some of the most widely recognized being the speed of light in vacuum c, the gravitational constant g, Planck's constant h, the electric constant epsilon 0, and the elementary charge E. Physical constants can take many dimensional forms. The speed of light signifies a maximum speed limit of the universe and is expressed dimensionally as length divided by time, while the fine structure constant alpha, which characterizes the strength of the electromagnetic interaction, is dimensionless. Dimensional and dimensionless physical constants. Whereas the physical quantity indicated by any physical constant does not depend on the unit system used to express the quantity. The numerical values of dimensional physical constants do depend on choice of unit system. Therefore, these numerical values are not values that a theory of physics can be expected to predict, because their units cancel. Ratios of like-dimensioned physical constants do not depend on unit systems in this way, so they are pure dimensionless numbers whose values any other civilization, anywhere, and at any time in the universe would predict. Additionally, all equations describing laws of physics can be expressed without dimensional physical constants via a process known as non-dimensionalization. But the dimensionless constants will remain. Thus, theoretical physicists tend to regard these dimensionless quantities as fundamental physical constants. However, the term fundamental physical constant is also used in other ways. For example, the National Institute of Standards and Technology uses the term to refer to any universal physical quantity believed to be constant, such as the speed of light c, and the gravitational constant g. The fine structure constant alpha is probably the best-known dimensionless fundamental physical constant. Many attempts have been made to derive its value from theory, but so far none have succeeded. The same holds for the dimensionless ratios of masses of fundamental particles. With the development of quantum chemistry in the 20th century, however, a vast number of previously inexplicable dimensionless physical constants were successfully computed from theory. In light of that, some theoretical physicists still hope for continued progress in explaining the values of other dimensionless physical constants. It is known that the universe would be very different if these constants took values significantly different from those we observe. For example, a few % change in the value of the fine structure constant would be enough to eliminate stars like our Sun. This has prompted attempts at anthropic explanations of the values of some of the dimensionless fundamental physical constants. How constant are the physical constants? Beginning with Paul Dirac in 1937, some scientists have speculated that physical constants may actually decrease in proportion to the age of the universe. Scientific experiments have not yet pinpointed any definite evidence that this is the case, although they have placed upper bounds on the maximum possible relative change per year at very small amounts. It is currently disputed whether any changes in dimensional physical constants such as g, c, h, or epsilon 0 are operationally meaningful. However, a sufficient change in a dimensionless constant such as alpha is generally agreed to be something that would definitely be noticed. If a measurement indicated that a dimensional physical constant had changed, this would be the result or interpretation of a more fundamental dimensionless constant changing, and which would be the salient metric. From Barrow, an important lesson we learn from the way that pure numbers like alpha define the world is what it really means for worlds to be different. The pure number we call the fine structure constant and denote by alpha is a combination of the electron charge, E, the speed of light, c, and Planck's constant. At first we might be tempted to think that a world in which the speed of light was slower would be a different world, but this would be a mistake. If C, H, and E were all changed so that the values they have in metric units were different when we looked them up in our tables of physical constants, but the value of alpha remained the same, this new world would be observationally indistinguishable from our world. The only thing that counts in the definition of worlds are the values of the dimensionless constants of nature. If all masses were doubled in value, you cannot tell, because all the pure numbers defined by the ratios of any pair of masses are unchanged. On December 13, 2012, physicists reported the constancy, over space and time, of a basic physical constant of nature that supports the Standard Model of physics. The scientists, studying methanol molecules in a distant galaxy, found the change in the proton-to-electron mass ratio, mu, to be equal to times 10⁻⁷ at redshift z equals 0.89, and consistent with a null result. Anthropic principle. Some physicists have explored the notion that if the dimensionless physical constants had sufficiently different values, our universe would be so radically different that intelligent life would probably not have emerged, and that our universe therefore seems to be fine-tuned for intelligent life. The anthropic principle states a logical truism. There are a variety of interpretations of the constant's values, including that of a divine creator, or that ours is one universe of many in a multiverse, or even that, if information is an innate property of the universe and logically inseparable from consciousness, a universe without the capacity for conscious beings cannot exist. Table of universal constants. Table of electromagnetic constants. Table of atomic and nuclear constants. Table of physico-chemical constants. Table of adopted values. Natural units. Using dimensional analysis, it is possible to combine dimensional universal physical constants to define a system of units of measurement that has no reference to any human construct. Depending on the choice and arrangement of constants used, the resulting natural units may have useful physical meaning.